Welcome to lecture 38 on polar area. So in this lecture, we're going to be finding the area between polar curves. So let me start out here with a drawing. So we're going to suppose R is a region bounded by a polar graph. So R is going to be equal to f of theta. So I'll go ahead and draw that equation right here. So this, let's pretend that this graph right here is R equals f of theta. So we have that graph. And also, the region is bounded by two rays. So theta equals A, and another angle theta equals B. So I'll go ahead and mark that on my graph as well. So this ray right here is going to represent theta equals A. And then I'll draw this one right here. I'll just say that this is theta equals B, going from the origin here, or the pole, to this right here. So we have our region, R. So it's going to be this sector right here that's trapped between the curve and the two rays. And suppose that this function that we're given is also continuous. And the way that we're going to name the angles is such that A and B are no more than 2 pi apart for their angle measure. So we have this going on. So if we were to take this sector and we were to take slices, like think back to calculus 1 with your rectangular slices here under the curve. If you took smaller and smaller slices here, just like this, where you could think of the delta x this time as the change between the angle. As this becomes smaller and smaller, you could use the idea of Riemann sums to get an exact area formula using the integral. So that's what we're going to do here. So we're going to use the idea of Riemann sums and the fact that the area of a sector of a circle is this formula right here. We can combine these two ideas and arrive for the area formula for this bounded region using integration. So the area formula that you need to know is going to be the polar area is the integral from A to B. So these are our two angle measures. 1/2 r squared d theta. And this is where r is equal to f of theta. So this is our area formula using the calculus of the area of beneath the polar curve. OK, so we're going to use this today, and we're going to do a number of examples where we calculate the area between polar curves. So our first example is this right here. It's what is the area enclosed by one loop of r equals cosine of 2 theta. So I spent time in a previous lecture, and all we did was focus on what the parent graphs for the polar curves look like. And now this is where this is going to come into play. If you know those graphs very well, then it makes your pictures for this and the work that results from them much easier. So I encourage you, if you don't know your polar graphs very well, you should go learn those first and then maybe tackle this lecture. So right away, I would want to know what this polar graph looks like. And we learned in a previous lecture that this is actually a rose. And further, it's a rose that has 4 petals. And one of the petals is centered right here. It's symmetric on this axis right here, what we would normally say is the x-axis. So the drawing looks like this. We have a petal that looks like that. It goes out to a unit of 1 because A in this instance is 1 in front of the cosine. And then we have 4 of them, and they need to be equally spaced. So I have another one that's opposite, going just like this out to 1. And here's 3 and here's 4. I don't have the best artistic ability, but there's my rose. I wasn't supposed to draw this petal so large. They're all supposed to be the same size. And we want to know what the area is enclosed by one of these. So an idea that I'm going to keep bringing up a lot in this lecture to also make your life much easier is the idea of symmetry. These polar graphs have a lot of beautiful symmetry. So when you're doing integration and you're trying to figure out, OK, how much area do I have, you could use the idea of symmetry to make your work easier by picking different bounds for the integral, or just viewing the object in a different way. So for example, if there's 4 of these, and I only want the area enclosed in one of them, then I'm focusing on just this petal, because all the petals are the same size. And even more than that is if you cut this in half horizontally, all I would need to do is find the area from, say, here to here if I'm talking about my theta, or from here to here. So I could say this is A and this is B. And if I find the area under the polar curve of just from the center to B, that's half of the area of what I need. So I could just start at theta is 0. That's this angle. And then what I need to know is I need to know what angle is this going to be to get from the halfway point of this petal all the way up to the first part. So to find that, what a common calculation you're going to do is you're going to set r, the curve, equal to 0. Because you want to know when that polar curve tensions back into the center again. That's when one of those loops is complete, right? So you want to know all the spots. You'd like to know all the spots where r is 0 here so that you get that spot where it tensions back into to the center. So we need to solve this equation. Another thing that comes up, all these things are coming back now. You have to be really good at your trig equations. You've got to be good at your unit circle. So make sure you review that as well. I want all the spots where 0 is equal to cosine of 2 theta. That lets me know that I need 2 theta has to be pi over 2 plus or minus some multiple of pi. So at pi over 2, we know cosine of pi over 2 is 0. So I need this to be true. That means my angles need to be, if you divide both sides by 2, they need to be pi over 4 plus k pi over 2, where k is just some integer. So for k, an integer. So let's go ahead and find what these two angles should be so that r is equal to 0. So using this expression, I'm going to plug in different integers for k. If I plug in -1, for example, if k is -1, if you plug this in, you get pi over 4 minus pi over 2 is negative pi over 4. And that is what this angle measure is. This is the first, this is the angle measure below 0 here, where you tension in to 0. It's negative pi over 4. And then this one, because it's symmetric, b is actually equal to pi over 4. And that's where when you plug in k equals 0, you get this one. And they go on and on for forever on either side. But the ones I'm focusing on are just these two that are within 2 pi of each other. So this is my a, and this is my b, I guess, that I was talking about before. They're within 2 pi of each other. And they both have r equal to 0. Go ahead and write down a formula for the integral here. So my area is, the way there's a couple ways I could do this. I'm going to show you a direct way here. So to integrate over this whole petal, I need to go from negative pi over 4 to pi over 4. And then following my formula, I would have 1/2 r squared, which this time it's cosine squared 2 theta, d theta. So following the formula exactly, I would integrate from negative pi over 4 to pi over 4, and I would get all of this first petal, and I'd be done. The alternative to this is that you could set it up in this way. You could start right directly on this axis, like I said, and just do half of it. So you could say, well, the area is going to be 2 times. So you're using symmetry here. I'm going to do the top half, and I'm just going to remember to double it. So I'll put 2 times the integral. And now I'm starting here, directly in the middle. So this is from 0 to pi over 4 of 1/2 cosine squared 2 theta dx. So that's yet another way. And notice when you multiply both by 2, this is an easier calculation. But these will both give you the exact same answer. So what is that answer? I think you should do that as an exercise and check if you remember how to integrate using trig functions. For both of these, the answer that you're going to come up with is pi over 8. So you should give that a shot. Make sure you remember how to integrate these trig functions. Let's focus on this next one now. So we're going to use this graph to draw the picture first. I'd like to find the area that lies inside this equation and outside this equation. So first, you need a very good drawing. So you would be able to identify at this point what type of graph this is. This is a circle. And because it's a positive sine circle, most of it's going to be in the positive y section of the graph. What is this? This is our cardioid. So I'll label this cardioid. This is our heart. And this is also mostly in the positive y section because I have a plus sign here. It's also a cardioid because both of the coefficients are 1. They're the same magnitude. OK, so let's draw a picture of what it looks like here. So first, the circle. That's easy enough for me. The diameter is 3. So I need to go here, 1, 2, 3. That means the radius is 1.5. So if I want to kind of orient myself, I know I need to go about 1.5 in either direction. Here's my attempt at a circle. That's it right there. So that's one equation. Now I need to draw the cardioid. And using the features of this graph, what I need to do is I need to look at A, which is 1, and B, which is 1. So to do the cardioid graph, what I'm going to do is I'm going to first remember that I'm going to be drawing most of the heart on the positive y because we have plus sign. How far up do I go? Well, the distance is A plus B. That's how far up you need to go. So A plus B this time is 2. So I'm going to mark this off at 2. That's the max of my cardioid right here. And then I'm going to mark 1 on either side because I know a cardioid will meet at the pole to create that heart shape that goes in. And the pieces of the heart that go out like this, that distance is A, which is 1. So now putting this all together, the graph looks something like this. It goes like this. And then you have a symmetric piece on the other side. So we have this heart that's going inside the circle. It crosses when you're 1 away on either side down here. And that's what the picture looks like. And now I'd like to shade the region that is inside the circle, but outside the cardioid. And that's right here. It's all of this. It's all of this stuff right here. And I'm really interested in the spots where they intersect. So here's one of them, and here's the other one. So I'm drawing those rays that shoot out here where the heart meets the circle. So it's this spot and this spot. And it's symmetric, right? All of this is symmetric. So we're going to use that to our advantage in a second. Now I'd like that to calculate what that area is. This is my A, this is my B. The area formula for this one is, well, first, I need to make sure that I'm inside the circle. So the area of everything that's inside the circle is 1/2. And it's going to be r squared. So my circle this time is 3 sine theta squared. So that is all the area that is inside the circle. However, I need to remove the area that's inside the cardioid because I want all the area that's outside of the cardioid. I want to just leave this portion. So I'm going to subtract off all this area that I don't need that's inside the cardioid. So we're going to subtract off the cardioid equation squared. Just like that. And now what do I integrate over? Well, the most basic approach you could do is you could figure out, well, where do these intersect? We need to know where these two graphs intersect right here and here, and then I'd have my total bounds. So let's look at their intersection. I'm going to set the circle 3 sine equal to the cardioid, 1 plus sine. I'm going to get 2 sine theta is 1, or sine theta is 1/2. And here you have to be really good at your unit circle. You need the one that's in the first and the second quadrant. What theta values are those going to be? And remember, they can't be more than 2 pi apart. You can't do that. So a few of these answers that you could get would be pi over 6. And then in the one that's in the second quadrant over there, what we need is also 5 pi over 6. Remember, there are many solutions to this, but I need to grab two that are within 2 pi of each other. So I know this is pi over 6. I know this is 5 pi over 6. So one way I could finish writing this integral is I could say this goes from pi over 6 to 5 pi over 6. That's fine. However, I'm going to stress again. My name is Stressy. I'm going to stress again. This is a really nice symmetric region. If you draw on this, you can see the symmetry. What happens if I cut it in half like that? Then I know if I integrate from pi over 2 to this new angle measure, we'll call it c. What happened to my pen? OK, there we go. Then this is half of what you need, and you would just double it when you're done. Well, what is that angle between pi over 6 and 5 pi over 6? That's pi over 2. That's directly in the middle of this. You can even see it because it's the vertical up and down. So another way you could write the area formula for this is you could say, well, OK, well, the area is also 2 times, and then it's 1/2, and you just integrate from pi over 6 to pi over 2 of 3 sine theta squared minus 1 plus sine theta squared d theta. And this will get you the exact same answer as this one. And sometimes this simplification or noticing this symmetry idea really does make the problem much more straightforward, or at least the calculation much more straightforward. Now, I have some space left here. I could do a couple of the calculations now, like the actual specific stuff. But this is the stuff that you learned back in Unit 1. So I'm trusting that you have a good foundation in this. I'm going to get you some of the way there, and then I'm going to supply you with the answer because I want you to also check that you remember how to do all that stuff. I'm going to start with the second one here. We're going to do this one. So we're going to multiply both of those out, so that's gone. We're going to simplify this as much as we can. So this is the integral from pi over 6 to pi over 2. This is 9 sine squared. And this, if you FOIL this out, it's going to be minus 1 plus 2 sine theta, and then minus sine squared theta. And I'm trying to be careful not to go off the screen there. Let's go down here. I see I have some more room. So this is the integral from pi over 6 to pi over 2. I can combine these, and I have now 8 sine squared theta. This would be minus 2 sine theta, and then minus 1 d theta. What you would need to do from here is you need to use that substitution we were using back in lecture 3 or 4 for trig integration. Remember that sine squared, you're going to need to know the one for cosine squared as well. You needed it for this one right here to finish this problem. Sine squared is 1/2 minus cosine of 2 theta over 2. You need this formula because what you're going to do is you're going to plug this in for sine squared. And once you've done that substitution, you can finish the integration. So now for time's sake, I'm going to trust that I've gotten you far enough along so where you can use your prerequisite knowledge and finish this. So I plugged this in. The answer to this calculation, is going to be pi. So the final answer I get for that is pi. OK, so well, what have we done so far? We've gone through what the main formula is that you need for area of a polar region. We've utilized our knowledge of previous graphs to draw sufficient enough pictures to then find the area of polar regions. And we've constantly revisited the idea of symmetry as we've done each of them. I think the only thing I didn't completely cover are these little minor calculations, which I expect you to do as well. Next, we're going to be looking at 2 more examples of finding polar areas. I will see you soon for that. All right, let's look at 2 more examples. So I encourage you to pause the video and try both of these yourself. Draw the pictures as well. I'm going to draw the picture for the first one here, and I'm going to draw the picture for the second one here. So I'll get started on this. We're going to find the area inside both of these 2 circles. So this circle, 2 cosine, is going to be 2 in diameter. And it is mostly on the positive x side because it's positive cosine. So I'm going to give my best attempt at drawing this. So it looks something like this. That's my circle. And then for r equals 1, this is a circle centered at the origin. And actually, I have it drawn on here, like when you're doing your the polar graph. R equals 1 is that first circle. So I mean, I'm just going to kind of color over it again. But it's that. So you have the circle centered at 0, 0. That's r1 radius. And then this new circle I drew that's just off to the side. And what is the area I'm looking for? Well, if I'm inside here, but I'm outside there, you're going to shade in your area just like this. And my drawing is not great, but I can see that this is symmetric. You can cut this right in half, right on the horizontal. And then I just need to ask myself, oh, look, what are these intersection points? And I can grab whichever one I want. So here's the first ray, and here's the second ray right here where they intersect. So right away, I'm going to start calculating, OK, where do they intersect? Both of these r's need to be equal to each other. So if I'm looking for the intersection, I would like to say that 1 is equal to 2 cosine theta, which means 1/2 is cosine theta. And where are those spots in quadrant 1 and 4 where these are both going to be positive? Well, it's going to be pi over 3 and negative pi over 3. So two possible solutions are negative pi over 3 and positive pi over 3. There are other ones, of course, but I'm grabbing two that are within 2 pi of each other. And I notice the symmetry again. At the angle 0, you have half of the area that you need on the top and the bottom. So the way I'm going to approach this is I'm going to say, OK, well, the area for this one is going to be 2 times. And I'm just going to do the area of the top half here. I'm going to keep my theta positive. That's just a decision that I'm making for myself. So I need to be inside the 2 cosine graphs. So I'm going to take all of the area that's there. So this is going to be the integral from 0 to pi over 3. I have 1/2. And it's r squared, so I'm going to take 2 cosine theta and square it. But I need to subtract out the area that's right here that's inside the r equals 1 circle, because I want to make sure I'm outside of it. So I need to subtract off this area. So this is going to be minus r squared here is 1. And this is the integral that I'm working with. So let's go ahead and do the calculation. So 2 times 1/2, that's just gone. And then here I have the integral from 0 to pi over 3 of 4 cosine squared theta minus 1. So continuing from here, I'm going to use the formula for cosine squared. So this is a equals integral from 0 to pi over 3. I have 4 cosine squared is 1/2 plus cosine 2 theta over 2. And I still have this minus 1 here. I'm going to put my d thetas where they should be. And then now I can go ahead and simplify this a little bit. This is the integral from 0 to pi over 3. 4 times 1/2 is 2 minus 1 gets me positive 1. And then plus 4 times 1/2 is going to give me 2 cosine 2 theta. So this is what I'm integrating. Let's go down here, see if we can finish the problem by just squeezing it on this last line. Integral of 1 is theta. And the integral of 2 cosine 2 theta is going to be sine 2 theta. And that's it. I don't have to add anything else. So integral of 2 cosine 2 theta is this. And I'm going to plug in pi over 3 and 0. So if you plug in pi over 3, you'll get pi over 3 plus, and sine of 2 pi over 3 is root 3 over 2. And notice if you plug in 0 into both of these theta spots, you just get 0. So another really nice thing that happens when you use this symmetry idea is you can make one of the bounds 0, or just something easier to plug in, and then the calculation becomes easier. So this is the area between the two curves. I suppose that's the first example where I went ahead and did all the calculations for you. OK. So let's take a look at this last problem. We're going to find the area inside both r squared equals sine 2 theta and r squared equals cosine 2 theta. And these are both lemniscates. So from our other lectures, you should know that these both look like infinity symbols or figure 8s. the cosine one is centered right here along the x-axis. So because there's a 1 in front of both of these, I know that they're going to be 1 on either side. So here's my cosine one. I'm going to do my best attempt at a drawing here. So here's this one. I need it to be symmetric. So, okay, that's not great, but they're supposed to be symmetric on either side. To draw the sine of 2 theta 1, what I'm going to do to give myself some help is I'm going to draw a dotted line at pi over 4. And I know that the top of the figure 8 is, I'm going to have to shoot for that. So here's my other lemniscate. It's going to be symmetric around that line I just drew. And I'm just shooting so that the top of the infinity symbol ends up there. For me, personally, that's OK. I did my best, and I think that looks pretty good. So what is the region we're looking for here? It's this one plus this one. So we need the region that's inside both of them. Well, it's this region, and we're going to use the idea of symmetry again. If we can find the area of one of these, we can just double it. And that's going to be the area of the entire thing. So we see that at this point right here, the two curves intersect. So I would really like to know what theta value that is. So let's work on where they intersect. So the intersection is going to be found when these two curves are equal to each other. So they're both equal to r squared. So we'll set them equal to each other and find the intersection point. Assuming cosine 2 theta is not 0, I'll divide it over to the other side and say tangent 2 theta is 1. And then this means I would like 2 theta to be pi over 4 plus some multiple of pi. Because I know when I have tangent of some angle is 1, it's either going to be pi over 4 or 5 pi over 4 or some multiple. So this means theta needs to be pi over 8 plus some multiple of pi over 2. And I'm just going to say k equals 0 here, because I'd like to stick in the first quadrant. So this theta that I would like to name, I'd name this pi over 8. Because when k equals 0, I know that the theta I'm interested in is pi over 8. So now, using the idea that these two identical pieces can be further broken down into 4 identical pieces. So right here at pi over 8, you can break this like leaf here into 2 identical pieces. So in total, you have 4 identical pieces. We can write the formula for the area in this way. So we could say the area is 4 times, and then the area of one of these 4 slices, which I'm going to focus on just the bottom piece of this area. So this equation that's going from 0 up here to pi over 8, this one is our sine lemniscate. So this area is 1/2 integral from 0 to pi over 8. And then my r squared this time is the formula sine 2 theta, d theta. So notice when you're dealing with lemniscates, the equation's already squared for r for you, so you just can plug that in directly. And I'm going to take 4 times 1/2, and I'll get 2 integral. I'm going to go ahead and take care of the integral, actually. So what is the integral of sine of 2 theta? Well, that's going to be negative cosine of 2 theta, and then I would have you divide by 2 by the chain rule. And I'll evaluate this from pi over 8 to 0. So notice the 2's cancel. I have a negative in front. I'll plug in pi over 8 into cosine of 2 pi. So this is cosine of pi over 4, which is root 2 over 2. And then finally, I'll plug in 0 into cosine here, and I'll just get 1. So it'll be minus 1. This negative sign I had out front distributes, and I'm left with 1 minus root 2 over 2. So this is really using the idea of symmetry in its highest form, because I saw I had 2 identical pieces, and then within each identical piece, you have 2 halves of those 2 pieces. So really, I just needed to take 1/4 of this area and realize I can multiply it by 4. OK, thank you so much for watching. I hope all these ideas of trig equations and polar graphs didn't confuse you too much. We'll work on more examples as well in class, but until next time, please send me any questions you have, and have a nice day. Bye.